end behavior and finding zeros of polynomial functions. Here's some vocabulary that you'll want to be familiar with. The end behavior is the way that a function acts as it approaches infinity. The leading term is the term of the polynomial that has the greatest power. The leading coefficient is the coefficient of the leading term of the polynomial. Zeros are the inputs of the function that produce 0. And the degree of the function is the power of the leading coefficient. This determines the degree. Some symbols. The sideways 8 is the symbol for infinity. The arrow going to the right means goes to. X usually means the input of the function, and f of x means the function or the value of the function. When we're looking at a function, we need to know the degree of the function. And in order to know the degree of the function, we need to know what the leading term is. The leading term is always the term with the highest or greatest power or exponent. So if we look at the first function, x squared plus 2x minus 3, the leading term is x squared, and the degree is 2, since the exponent on the leading term is 2. For the next function, x cubed minus 6x squared plus x plus 5, the leading term is x cubed, and the degree is 3. Now for the other functions, the leading term is negative x to the 5th, and the degree is 5. And the last function, the leading term is negative 6x to the 6th, and the degree is 6. This is an example of an even degree function with a positive leading coefficient. And as you can see from the graph, it is a parabola opening up, and it has 2 zeros. The even degree functions have a leading term with an even power. That's why it's important to take note of the degree and the leading term. Now, when we're talking about end behavior, we're concerned with where the function is going, less where the zeros are. Where this function is going is positive in both directions. As the input increases, the function is increasing, which means that as x goes to positive infinity, the function goes to positive infinity. And if you look at the opposite direction, the function is going in the same way. So if the input is going negative or more negative, the output or the function or the values of the function are going positive. And so as x goes to negative infinity, the function goes to positive infinity. The idea with end behavior is, since we're talking about the degree of the function, the other exponents, for example, this exponent of 1 or this coefficient, has very little impact on values that are very large. So if we think of, if we were putting in a value of 3, the 2 times the 3 is very close to the x squared. And even the minus 3 does have an impact on that. And that's why around the zeros and the vertex, the parabola is more gradual. But as we put in larger values of x, let's say 1,000, then 1,000 squared is much larger than 2 times 1,000. And so that's why we have this steepness going as you get further away from the zeros. Now, let's look at the end behavior rule for an even degree function, but with a negative leading coefficient, like in this function that we looked at before with the degree. The leading term is negative 6x to the sixth. The degree is 6. Again, we're more concerned about what's going on here for large, very positive, or small, very negative inputs. Notice that the function goes down in both directions, so as x goes to negative infinity this way, then the function is going to negative infinity this way. And as x is going to positive infinity this way, f of x is going to negative infinity this way. Now, as you might have expected, it's going to be different for odd degree functions. This is a basic odd degree function, a cubic function that has a coefficient of 3. And notice that even though we still have some steepness going on here, we actually have a function that starts out or goes to the negative in one direction and goes to the positive in the other. So as x goes to negative infinity, f of x goes to negative infinity. As x goes to positive infinity, f of x goes to positive infinity. So you could think of, for the odd degree functions, the x goes negative, the output goes negative, the x goes positive, the output goes negative, positive. Now, remember that negative, or taking the opposite of something on a graph, would actually flip the direction. So, for an odd degree function with a negative leading coefficient, we have that instead of the function going negative, as we saw before, as x goes negative, the function is actually going positive now. And as x goes positive, the function goes negative. So using our notation, as x goes to negative infinity this way, f of x goes to positive infinity this way. And as x goes to positive infinity this way, f of x goes to negative infinity. Now the odd behavior rules that I've just shown you for these functions actually work for all odd degree functions. And the even degree function rules that I showed you also work for even degree functions. Now let's talk about what happens at the zeros. When we were working with quadratics, we talked about the zeros. We talked about the zeros because we wanted to know the solutions. Or if we had the function like f of x equals x squared plus 2x minus 3, we wanted to know what x was equal to when f of x, or the value of the function, was 0. So remember that the inputs of the function that produce 0 are also called the zeros. The real ones are the x-intercepts, and we're actually going to be looking at what happens when we have imaginary zeros as well. So let's look a little bit more into the concept of zeros. There's 3 things we need to remember about zeros. Instead of looking at the ends, as we did in end behavior, we want to look at the zeros, or the x-intercepts. Another thing to remember about zeros is the number and type of real zeros depend on the number of x-intercepts. And so in this function here, we're actually going to have 2 real zeros because we have 2 real x-intercepts. Or we actually have x-intercepts because if you have non-real x-intercepts, that isn't going to actually cross the x-axis. If we have non-real or imaginary zeros, they will always come in pairs. So if we look at this function, remember we had 2 real, and this is actually a 6-degree function, and so that means we're going to have 4 imaginary. Now I'm going to talk more about having the imaginary in just a moment, but I want to talk more about this concept of the imaginary zeros that come in pairs. Think for a moment that you have some number that equals, or the square of a number equals -9. So the number that when multiplied by itself is equal to -9, there's 2 of them. There's -3i and there's +3i. Another way to look at it is if you had a negative discriminant in a quadratic function. Like let's say you got something like this, -3 plus or minus the square root of -20 divided by 2. Now notice that even though we have a negative here, this means imaginary zeros as we learned with the properties of the discriminant, but this plus or minus is always going to give us 2 imaginary solutions. Remember, we learned that when you have a negative discriminant, you're always going to have 2 imaginary solutions. So, no matter what function you're looking at, no matter what degree, if you have any imaginary zeros, they have to come in pairs because of this property of the negative discriminant. All right, so we kind of talked about this 6-degree function and how many numbers it could have. Now, since it's a 6-degree function, then the total number of zeros, or the maximum number of zeros that it could have, is 6. There are 2 x-intercepts, and so there are going to be 2 real zeros and 4 imaginary zeros. 2 plus 4 equals 6. Now for this x squared. The total number of zeros is 2, and the total number of x-intercepts is 2, and so the number of the zeros, number and type of the zeros, is 2 real zeros. For this cubic function, the total number of zeros that we could have is 3, and the total number of x-intercepts is 3. And so there are 3 real zeros. As you can see from the graph, we have this kind of loop-de-loop thing going on here. Well, okay, maybe it's not a loop. Maybe we want to think of it more of a curve. But you can see that here it goes through, and here it kind of makes another change. That tells us that there's going to be some imaginary zeros. The other thing that tells us that there's imaginary zeros is that this is a 5th-degree function, and so the total number of zeros could be 5, but there's only 1 x-intercept, which means there's going to be 1 real zero and 4 imaginary zeros. 1 real plus 4 imaginary equals a total of 5. Now, we're going to look more into this. So let's look and graph some of these functions here. the first function, 9x cubed plus 10x squared, minus 17x minus 2. It's a third degree function. So there's going to be 3 zeros, and you can see that we have 3 x-intercepts, and so this is going to have 3 real zeros. This x to the 5th. Very much like the other one, we have 1 x-intercept, which means 1 real zero, but since it's a 5th degree function, it has to have a maximum of 5 zeros, and so this is going to be 4 imaginary. And here we have an x to the 4th, or a 4th degree function, which means we have to have 4 zeros. We can see there's 2 x-intercepts, and so there's going to be 2 real zeros and 2 imaginary zeros. And finally, another 5th degree function. You can see that we have 1 real zero and 4 imaginary. So, I have some questions for you to email. Question 1. Why do imaginary zeros come in pairs? Question 2. Why are the solutions of the function sometimes referred to as the zeros of the function? That was a question on the last test. Question 3. Explain the process of finding the end behavior of a function. Make it brief. I don't want non-convoluted paragraphs. And question 4. Why is the end behavior determined by the leading coefficient?